Okay, so in this video, we're going to talk about action potential conduction. Okay, so notice that I've got two neurons here, and these are just the axons. Obviously, it's not the full neuron, but this will hopefully get the point across. So this one is non-myelinated, and then the bottom one, so just so we're clear here, we've got this dividing line, and then this one is myelinated. Okay, they're the exact same. The only thing that's different is we've got this myelin here on this neuron, right? And so remember that these these gaps here are called nodes of Ranvier. Okay, so let's talk about an unmyelinated neuron first. So we've got this unmyelinated neuron up top. And so what's going to happen is we're just going to say that our action potential comes. Okay, so here's my little action potential. That's what that little squiggly line signifies. And so what happens is when the action potential gets to each part of the axon, it depolarizes, repolarizes, and hyperpolarizes that part of the axon. And so what happens is action potential comes here. We're just going to say these are sodium channels. Those sodium channels open. And so what happens is sodium goes in, sodium goes in. This leads to depolarization inside, which then opens these channels. More sodium comes in, so on and so forth. Okay. Now, as sodium comes in, and I'm not exactly sure how to draw this, so we're going to try. So here we've got lots of sodium outside, a little bit of sodium inside, right? So we've got this concentration gradient. So as sodium comes in here, one of the things that you can think about is that sodium and other positive charges are being repelled. And so this sodium moves down. Well, by moving down, that's actually depolarizing that part of the cell. And so now what happens is, well, we can get, whoops, is that we can get sodium to go in here. Those channels open, so sodium goes in here. And the sodium that's entered keeps getting pushed this way. And so remember, positive charges repel positive charges. And so as a result, what happens is, like I mentioned here, we depolarize this part, which depolarizes this part, this part, this part, this part. And eventually we reach the axon terminal. And if you remember, the axon terminal is where we release a whole bunch of neurotransmitters. So here, we'll just draw our axon terminal there. Okay. But the important thing to remember is that in an unmyelinated neuron, we have to depolarize every little piece of the axon, and this takes time. Okay. All right. So this is relatively slow. Okay. Now, in a myelinated neuron, the only places that really are depolarized are right here, these nodes of Ranvier. Okay. And so what happens is somehow, some way, and there's a lot of ways that it can happen, and we're not going to get into the specifics here, but some sort of graded potential is going to open up these sodium channels. And notice there's a couple things I want you to notice here. One, we've only got sodium channels in these nodes right here. And two, notice that up here they're kind of spaced out. Okay. Well, in the nodes of Ranvier, we have a high concentration of these sodium channels. Now, there's also the potassium channels and everything else that we've talked about with an action potential. Okay, so those all still exist. We just kind of focus on the sodium channels because sodium influx is what causes or what leads to that depolarization. But if you think about it, we have to have repolarization to occur. Otherwise, what's the point? Okay. And so what happens is that when we depolarize this part of the cell over here, we're going to end up opening a lot of gates really quickly, okay, because they're so close in proximity to each other. So now we have a whole bunch of sodium come in, right? And so it's going to go through all these, all right? And just like up here, there's sodium in the cell. But when you have all of this positive charge coming in, this sodium wants to run away, run away, run away. But because we bring so much sodium into the cell at these nodes so quickly, that produces a large force that repels the positive charges that are already in the neuron. And so as a result, these sodium ions and other positive charges get pushed down here to the next node. Well, what do we have at the next node? Well, we have more sodium channels. Okay. And so when this sodium moves down, that part of the neuron becomes depolarized. These sodium channels open. We have a whole bunch of sodium come in. Okay. And depending on where we're at on the axon, Either we're going to push more sodium into the cell, it's going to depolarize the cell, or we might eventually be at the axon terminal. And similarly, here we have the neurotransmitter release. Okay. And it's important to remember this is very fast. Okay. This is something like, and you're not, this is never anything I'll ask you, but something like 100 meters per second, whereas this might only be 1 meter per second. Okay. Another thing to think about, or another thing to know when it comes to action potential conduction that I can draw out is the diameter. Okay. So here's my narrow or my skinny neuron. Here's my fat or wide diameter neuron. Okay. And you can think about this in terms of straws. We've talked about flow, we've talked about resistance. Well, narrow, something that's narrow, that leads to high resistance, and that leads to low flow. Whereas here, wide leads to less resistance. If I have less resistance, I have increased flow. Okay, and the same is true in these neurons with ions moving. So we've got these two neurons. The only thing that's different, their lengths are the same. It's not the length that matters, it's the diameter. And so large diameter neurons have less resistance. There's more places for the ions to go because there's less resistance. And so as a result, it's easier for an action potential to travel down the axon, right? The other thing that I'll mention here, but I can't draw this out, or I don't know how to draw this out, is temperature. Temperature is just a measure of kinetic energy or velocity of molecules. So high temperature, molecules are moving faster. Okay. Low temperature, molecules are moving slower. So if we have high temperature, that means molecules are moving fast. So high molecule velocity or speed. So that leads to increased action, potential, conduction, velocity. Okay. And then hopefully you can see that the reverse would be true. Lower temperature, lower velocity of molecules, so the action potential can't travel as quickly. And so with that, there we go, action potential conduction.